Tomcat has been very involved in EDA, semiconductors, electronics, embedded systems, software, and IoT applications. He is currently the chair of the GSA Trusted IoT Ecosystem Security Group, and it's an industry-wide collaboration, which he'll touch upon in his presentation. Prior to the GSA, he led the trust chain business at Siemens and has worked in a number of various positions across the industry at many firms. And with that, we welcome Tomcat.
Thank you, Ira, and thank you, everybody. I do understand that some of you here in the audience today may be members of the GSA ties and may have been involved in some of the things that we will discuss today, in which case, feel free to chime in. Now, basically, what we're going to go today is going to cover a little bit about the operating model of ties, because we're a bunch of technical people, but we're trying to actually solve operational and business problems in order to accelerate adoption. Then we're going to go to the subject that we all care about, which is tested traceability and test data, and how do we actually track that. So the motivation of GSA ties started after spending many years in trust chain, first at Mentor Graphics, trying to do it from the chip outward in the supply chain. And then later on, when Siemens bought Mentor Graphics, we're trying to do it from the device inward back to the chip. So we learned a lot of things, and we learned the most important lesson that traceability in the supply chain is an ecosystem problem. No one company can solve that themselves. At the same time, we got very interesting times with the geopolitical issues, the supply chain issues, supply chain resilience. We hear it every day, primarily because of logistics, but the word supply chain security comes across all the time these days, particularly after the CHIPS Act was signed. And our thesis is that lack of visibility in how all the parts came together into the system is basically the major risk. And that is as a result of the disaggregation of the value chain, unregulated distribution channels, and of course, organizational silos. It's not like when I started at DEC, I was a chip designer, engineer, an EA developer. I manufactured my chips, I debugged my wafers, I packaged them together chips, then I got them into a system, and then I shipped the system to connect the DECnet. I did everything as an engineer when I started about 30 years ago. But you cannot do that today, it's disaggregated. So the supply chain traceability of ICs and test data, and that's together, it's key for quality, reliability, and security. In fact, this started as security, but now we put the emphasis on quality and reliability because security can be an add-on. It's another vulnerability. The GSA ties focuses into more of a business ecosystem strategy to incentivize traceability. There's 300 GSA members that range all the way from chips all the way to cloud, hyperscalers, edge applications, etc. Of course, we're more chip heavy, but we're growing in terms of systems of vendors, etc. And the idea is to create a collective ecosystem IQ, as if we were one IDM, if you will, virtual IQ, and essentially drive a digital thread for trusted electronics and digital twins. And we do that by creating interactions in what we call a platform-based business ecosystem. So the mission is to essentially develop a collaborative ecosystem that has every vendor in the continuum from EDA, IP, IC Foundry, OSAT, et cetera, all the way to PLM and the edge vendors, and to promote end-to-end solutions. But there is a catch here. We're not doing it from the left of the supply chain to the right. We're not doing it from a chip to the end application. We're doing it backwards, from the end application to the chip. Because when we do that, we can actually have visibility on issues that affect the chip, like functional safety, for example. So the goal is to drive a shared success model for promoting secure and trusted digitalization solutions. There's no way you can have traceability without digitalizing the supply chain. And if we can actually do that, essentially everybody in the stakeholders become connected stakeholders. So we have connected chips, connected devices, connected systems, and connected applications. And the more connected we become, the more the security vulnerabilities. But on the other hand, we have an opportunity to create digital threads of data for creating digital twins. And the idea is to enable, facilitate new services, revenue streams, and scalable business models for everybody who participates. We grow in the business ecosystem where stakeholders add value in a standardized way. You can have essentially GSA ties, you have competitors, but what we try to do is we try to solve problems that are common across those competitors, and we try to add value in a very standardized way. And because we're very technical, what we have is the classic concept of an elevator pitch, if you will, that is used in startup competitions in order to create the investment rationale behind it and convince the executives why they should invest. And of course, we promote a shift-left approach where we basically say, start from a use case, from the end application, and get back all the way to the chip. Value, the idea is to accelerate transformation of the value chain, both in secure and trusted devices, which will also improve reliability and quality. And we essentially network a lot. We do white papers in conjunction that become essentially end-to-end operational specs. And then we've already seen that many of the members partnered outside of GSA to do proof of concept projects before they invest in large deployments. So the fundamental concept of IoT is that you're going to have lots and lots of enabling services and edge data devices serving many markets. And those will be fueled by essentially IoT devices and powered by trillions of chips on those devices. The first thing that I'd like to say to people is IoT is not about offering connected products. IoT is about being connected to your products. And that's where the smart connect supplier is. Because if you're connected, you're going to have a lot of benefits from visibility, lifecycle management, support costs, lower OpEx. But when you become connected, you open up Pandora's box in security, trust, and sharing of data. That data actually is very important because it contains data for reliability and security. So how do we evolve traceability solutions? And that's my favorite use case. Some of you may have seen that slide. And I use this as a master use case for a couple of reasons. It captures both quality, reliability, and security. And it captures the fact that you may have all kinds of tests in the supply chain, with the exception of key injection that is not a test, but it still opens up something to do in the chip. And those tests essentially are opportunity to collect data on the one hand, but they're also opportunity for the hackers to put a little listening device while the chip is powered up and basically extract keys and do things that can eventually hurt and attack the chips later on in the fleet. So, but starting with the security and reliability, the classic problem is that, I discovered a vulnerability, a bad chip in a car, and we're trying to basically go backwards to find the root cause. And it goes all the way back to the foundry, and eventually the foundry figured out it was a bad lot. So it was a bad lot, but now we have found this problem post-singulation. So how do we trace where all the other dice went? Known good dice or unknown good dice and where they went, okay? So that's the traceability problem. At the same time, we have all kinds of other things that pop in, which is security-related issues from reverse engineering of production gray markets, counterfeits, IP theft. So those are vulnerabilities on top of quality and reliability vulnerabilities that could use the same infrastructure in terms of traceability. And in fact, the economic motivation would be to do that in order to achieve economies of scale. So how do you actually solve that problem? Both downstream traceability and then upstream traceability, and not spend 9 months to find the unknown bad die, but be able to do it instantly or almost instantly. So the answer is that basically the world needs to move to what we call some identity inside the chip. There are two kinds. A fingerprint, which is typically a PUF technology and is used for authentication. And then another kind is what my friend Mark is going to talk about, from proteanTecs, which is more and more a DNA-like, that from the process parameters, you can create a unique signature, and that could actually help a lot, not only for authentication, but also genealogy. But if you can actually put those in the design, all right? And then you do your initial wafer test, there are mechanisms that you can use the DFT approach together with the fingerprint to essentially enroll that chip to a server. And the enrollment process is very analogous to you opening up a bank account. You share your secrets for the first time, and then that's it. The server or the bank knows you. And when you go to a different browser, may not recognize you, will ask you your secret questions. It's exactly the same thing with the chip. The only complication is that between the chip and the cloud or some other server outside, you have what we call a lot of middleware, testers, PCB, systems, and of course the equipment, the cars or the airplanes, right? But at the end, there's a middleware in between that can establish that secure protocol. And once you have established that before you singulate the die, or even after, perhaps during the final test, then you have a basis for traceability to the extent that, you can connect that with the rest of the operation. Because the chip supplier, if you don't do that, you'll never be able to know, particularly if you have distributors, where that chip ends up and who is using it. The other thing you will not know is who turns the power on and what they do when they do that. So part of the fingerprint of the security mechanism will be to potentially, during test, to say you got a gas tank of 1 million cycles for your test, but once you exhaust that, the chip is automatically disabled and it will be enabled only when it self-authenticates downstream in the supply chain. At the same time, with this approach, we can start actually creating, collecting test data, not only from wafer testing, but every place in the supply chain. Provided, of course, there was an infrastructure to do that, which it does not today. But obviously, I'm implying that there's going to be some sort of blockchain. We'll talk about it. But the most important thing is the digitalization with respect to the operations that follow processes in managing that particular chip. And that means engineering is involved, operations, production, procurement, accounting, because traceability is, you need to link that identity with the serial numbers, with the SKUs that you provide and everything. And eventually, as it goes in the supply chain, you need to provide a certification, which is not much different than the classical certification that you see in 64.2.4 in automotive, but now it's for security. All right. So that's the grand vision. And if you can actually put all that together, we don't have that today. That's a big vision. And then, to the extent that you can have all these APIs for all these tests, basically is enabling applications running in the cloud, you can have full traceability with full supply chain analytics. But more importantly, another business benefit is that you're going to have full configurability when the device is onboarded to the region, to the end application, to the cloud, whereby you provision it relative to the regulations and characteristics and features that you need to have. But the important thing is that once you have that infrastructure, everything that is done under test becomes an opportunity to collect the data, put it in certain places, and then make it available to participating stakeholders that have an interest for that data. Okay, so before we go there anywhere, this is the grand case that we want to solve today, all right? And the way we're going to do that basically is by saying, all right, we have an ecosystem of companies that consist of semiconductor space, the device and system space, and the IoT application space. And they're all connected because they hand off stuff from one another for different applications. And I'm missing my airplane here. I don't know what happened, the demon of graphics. GSA has 300 members, very well known in the board of directors from companies like Intel and, and Cisco and AMD, et cetera. Represents about 550 billion industry. I'm going to give you a quick overview about the operating model because it's very important. We have developed an architecture that is open and participatory. Anybody can come in and add value in their specific subject matter domain, whether this is PCB or system, adding the OS or the edge. But we have some certain rules that, everybody has to follow in order to have a consistent model for success. And whatever we do, maximize the interactions, because the network effects is what broadens the IQ in the whole ecosystem. The most amazing thing about GSA ties is that we have people from the same company. One is from the design and the other is from the IT managing subcons, and they meet for the first time here at GSA ties. And they said, I never understood how much security is intimately related and quality related to traceability. And then the idea is to build a digital thread where basically you're going to have handoffs, which requires some digital transformation. And if you actually do it right and you trace all that stuff, then you have the opportunity now to create data at the end applications, which will allow you to essentially do trusted analytics. And then eventually that data may go to different parties, whether this is a chip supplier, the PCB, or the system, for analysis and potentially training and potentially the ability to improve their products in the next generation directly from feedback in the field. And that is basically the grand ecosystem value proposition. Now, any questions before I proceed? This is the operating model. This is like how we work. Okay. Now, just at a high level, you can go to the GSA ties and get the orientation and understand the details. But at a high level, we are not pushing standards. We're creating a standard operating methodology, but not technical standards. So we define end-to-end use cases. We usually get the OEMs to provide use cases as a repository. We form teams that have EDA supplier, IP supplier, chip supplier, system supplier, packaging vendor, cloud vendor, PLM vendor, and then the team creates a solution end to end, and then we publish it, and we actually make it available to standards bodies that may be referenced, whether this is SEMI or IPC or what have you. And then when they have an improvement, they notify us and we notify the ecosystem. So it's an awareness grand ecosystem. Everybody starts with a white paper, which is the basis to start networking, collaborating. There's different topics, but because we are very technical and those papers are targeting the executives of the members, we're trying to create this business of an elevator brief and an elevator pitch where we make it very business-like, and only the proposed solution in the middle becomes very technical. So if the executive sees that and gets to the technical point, he will pass it to his technical people. If the technical people see that, then they say, oh, I now understand the business case, I can convince my executive to invest. So use cases basically are typically, with the exception of some use cases are horizontal in the supply chain, they are vertical by market application. We describe an end-to-end solution, which is carried out by the collaborative team. And then the team has to articulate clear benefits and business value proposition. And it boils down to accelerating adoption, reducing OpEx cost of risk, increasing product value, and more importantly, how we're going to enable new revenue streams, because now we're going to have the ability to offer services, whether this is for quality, reliability, or anything that relates to data that will feed AI applications that we cannot even imagine today. So use cases, there's classification of them. The ones that are more prevalent right now is on the bottom here, because we're trying to build infrastructure where all the application markets will come as apps. Now, we do have some end application use cases, such as, for example, a multi-tenant solution, a cloud multi-tenant solution for automotive, under which the OEM or the chip supplier or the mechanic or my wife can go access the platform associated with my car, which is registered on the cloud, after that car basically is onboarded using the root of trust in the chip. So that's a classic and an application. In the market-specific use cases, you would have functional safety use cases in automotive. Also, they apply to aerospace. You may have certain use cases associated with how built infrastructure for industrial, and so on and so forth. But guess what? All of them rely on one very important thing, the stability of chip. And then in the ecosystem, we have a team of loyal people. Out of 100 contributors, maybe 20 are very loyal, that participate in many of those and also interface with the standards bodies.
So, Tom, a question from the audience, and you talked a lot about test data, but what about other types of data like inspection data and whatnot? How extensible, or what's the vision for the inclusion here?
The vision for the inclusion requires what we call the concept of digitalization, which is coming up in the next two slides, all right? Because every operation can digitalize its data, keep its data for itself, but have a mechanism to make that data available to other parties for a fee, of course. Data should not be free. And you'll see how. For example, I start with manufacturing. You have manufacturing operations, which is metrology data, right? And then you have test operations, which is test data. Those are two different data types that have to come from the trusted process. They are typically saved inside the enterprise, but we will show you how you can actually make them available on demand, all right? At least a vision of how we're going to go about it, to parties that are interested in having that data. And that is a fundamental, important part of traceability, because when I buy a chip, I don't want to have to retest everything. I don't want to have to redo something that was done in supply chain. Somebody has that data. So why not? Lockheed says, I'm paying you, I will pay you money, foundry, if you give me that data instead of me putting engineers to retest the chips, right? So the data becomes essentially the central piece of the ecosystem where everybody can extract value, and either by selling it, licensing it, or by consuming it. And this is now where we get into the trusted supply chain traceability and digitalization. This is the most important thing to understand, how we're going to bring the pieces together. You're not going to bring a solution end to end like this, because there's many companies and many experts. We compartmentalize it into, a domain that has the receivables, a process steps and deliverables, all right? And then we connect all these domains with the different experts. The fundamental premise starts in 3 markets where we believe there will be the leading markets in adding fingerprints, sensors, and security in the chip. And those markets will be pretty much automotive, aerospace, defense, and industrial, because they are lower volume, but higher value in terms of data, okay? You're not trying to squeeze essentially the area for everything. You're willing to put the extra circuitry to be able to get the analytics that you get later on, okay? And the idea here is that this process that you see in the middle is something that is an operating process that can be digitalized. So we have a digital asset, but the physical assets are delivered in actual manufacturing environment. The fundamental principle behind it is that you take the classic workflow that enterprises have for HR, finance, and sales and everything, and you bring them to the engineering department. You're not digitalizing the EDA flow. You're digitalizing the process of the functional process of the different departments carrying that EDA flow. So if you actually do that, all right, and you do it separately for each domain, because each domain will have their own gazindas and gazados and data and things that they care about, then you can start collecting this ecosystem like you. The next step is, how do you actually create that digital thread? Well, digital thread starts with something that we call zero-touch enrollment during manufacturing test, all right, to establish a provenance. And then digitalization is basically how you digitalize the steps inside an engineering operation or inside the manufacturing operation. And those steps basically are process steps, workflow steps, to put it simply, all right? And if you actually do all that, then you create a digital thread, and at that point, you can, all the devices that will have data all the way to the end, they can be basically collected, they can be filtered, they can be queried, and can be sent to the parties that care about whatever data they care about. Now, let's talk about digitalization very quickly. Digitalization basically is taking any operating process where you're going to have operating tasks and subject matter experts on those tasks, the red, the brown, the blue guy or girl. And essentially, digitalization basically means that you're going to introduce some anti-tampering mechanism, because the red person may be a rogue engineer, maybe a rogue person. You don't know that. Even though if you're a trusted supplier, you don't know that. So you have to basically be able to have the ability to add blockchain for anti-tampering, encryption of the data in and data out, and then secure access of that data through a key, all right? And of course, some certification for that data to ensure, from an attestation point of view, that whoever gets it downstream trust that this data came from a trusted party. Now, notice what we're describing here is the notion of security in the process and not in the assets. This is very important, all right? But if everybody follows the model, whether you have 3 steps or 1,000 steps, that you have a bill of material receivables and a bill of materials deliverables, and there may be zettabytes of data created, which you will never export out there. But if you index it and you add a little description of what you've done inside, to the extent that you don't want to disclose everything, right? Then that data can become queryable from a grander infrastructure, and then based on that ledger of data, if you will, then different you can create what we call a marketplace of trusted data producers and trusted data consumers. All right, and that applies to EDA design and of course manufacturing, both at the IC and the PCB and the system level. All right. And then if you can create the backward thread, for example, one of the people in the team is doing the backward thread in what we call virtual identifiers on E142, which many of you are familiar with, to be able to essentially have the ability to say, oh, I received this part. How do I know that I trust everything about it, including the data? So that traceability exists if you want to query it down. So that's the vision. And this is basically an extension of the entire supply chain that we submitted to NIST as an ecosystem strategy. NIST basically has pervasively penetrated the world with this framework called the cybersecurity framework, which is essentially a recommendation of how you're going to structure operationally inside the enterprise the process of security, all right? It's not any hard rules, but you have to follow certain methodologies. And on top of that, we have this digitalization concept with the identifiers. So all these metadata indices go to a local storage, and then eventually they'll put out to the cloud, and the same applies for everybody in the supply chain. And then in the handoff points, you have what we call cryptographic linking, because when you hand off data, that's the biggest vulnerability for people to intrude that data and mess around with it, or to intrude the chip and mess around with it. So that is a big, a 15-page document that we submitted to NIST. You can click on the link and go read more about it. But this is the fundamental ecosystem strategy that we're proposing between NIST, the EU CHIPS Act, and the US CHIPS Act. So very grand vision, but it can only be done by many companies. Okay, let's get to the stuff that you care about. All right, this is a white paper that is under development. Some of you here, I believe, Adam Cron may be here, are basically participating in that, and it has experts from test, EDA flow, testers, manufacturing, you name it. There's 20 contributors across the spectrum, all right? And the idea basically is traceability starts from IC design and manufacturing, and it starts by essentially injecting a subsystem during RTL design that contains the DFT, the root of trust tied to the DFT, and the identity generation. You may actually have also a verification IP model that will ultimately verify how the chip connects to the cloud and what are the possible intrusions you can have, et cetera. But more importantly, you're going to have this special vector for enrollment during the TPG for enrollment, all right? And then what happens is when you go to the fab, during probe test, if there is probe test, the in-circuit ID will be generated, and then other physical identifiers will be generated along the process and linked with it, all right? And then you hand off to the OSAT, where you're going to basically, or maybe the same operation where you're going to do the final test after the dies are singulated, and eventually you're going to add some virtual identifiers when you put them on the box and ship them. And during all that process, we need to basically collect manufacturing, test, and security data, and manufacturing comma, it should be a comma here. That means metrology, test data, and of course, security data associated with the identity. And if you actually do that enrollment right, whereby now the chip can go out in the wilderness and talk to a server securely, many of those problems that everybody's familiar with, counterfeiting, overproduction, et cetera, can be addressed, or at least can be detected if there was a situation like that. So basically, the idea is you put together with the DFT root of trust and the security, and then when you go to the fab, the test vectors come in, the power comes up, the identities are generated inborn in the chip, and then they come out as part of the test data into a local host next to the tester. You can also have a security model to make sure inside the tester to make sure that nobody messes with it. And then eventually you can go to the PCB. And from that point on, notice that we have here a little BIST that shows that you can collect data from the field and essentially get it to the cloud. Of course, this is a simplified picture, but the most important part here is that there will be lots and lots and lots of middleware APIs, being the tester, the PCB, and et cetera. And the process of digitalization basically says, I'm going to basically create that chip that will have the DFT, the root of trust, and the identity. I may put sensors, or as proteanTecs calls them, agent, because I want to collect other data from inside the chip. And one way to do it is through IJ tag, because now you can collect data on a per IP basis. And that's very important, because when you collect that data, you may want to collect it encrypted so that it's not available to everybody. The other part that we do is we actually create process identifiers so we know who did what when. Okay, then it goes to manufacturing, and in manufacturing you have the steps before the actual test where you may collect metrology data, all right, and that may be linked later on with test data. Okay, and then you do the wafer testing. At that point you have established some identities, and then when you do dicing and so in bare die sorting, etc., all that can be tracked. If the wafer was shipped directly to the OSAT and it was singulated, you got a problem. That means you got to create all these identifiers before you get to the final testing to link them, all right? So, and by the way, by linking the identifiers, the existing methods like the ECID and everything are linked with it. They are not becoming obsolete, because fundamentally we're linking an inborn in-circuit identity with all the other identifiers that exist today as standards. The important thing is that when you get the test data out in any format, you get the classical data of fail pass per die, but you also get a form of encrypted identity, a public key that can be used in the supply chain for other applications. And you can also get all the other data that you want, which in the enrollment phase, it will be very little. It will be just to test that you can get other data. But downstream in the field, you can open up securely the JTAG instead of fusing it and get all kinds of data using the classical, IGA tag approach that is being stored potentially into a memory inside the chip. We're not talking necessarily real time. We're talking also batch data that you collected during the operation of the chip over a period of a day or two, whatever. Okay, I'm rushing a little bit because I think that, I'm going to run out of time. Then you send the chip to PCB. And of course, in PCB, you have system design and you have all these operations and assembly. But what is very important to happen in the industry, and that's what we're pushing, is that every chip should have a fingerprint. And we're going to basically get, we're moving that direction. The microprocessor guys, the microcontroller guys, the memory guys will be the first to lead because they will drive essentially the whole ecosystem. And those basically will become the asset identifiers, and there will be a component trust score that is a combination of bill of materials, identifiers collected, metadata, certification, attestation. So everything that comes in is known. The thing that is not known, obviously, is resistors, capacitors, but there are companies like Cyborg that take care of that. And then you go through all these tests, and then you do the electrical test at the end. At that point, you have an aggregator of trust, bill of materials. You can create what we call a platform certificate. It can be 90% of the market is PCB today. Obviously, you have to do the same for heterogeneous integration, which is a little more complicated because you have connections between the bare dies, which are points of infusion and intrusion. You do essential attestation, you create a certificate, and then you can ship that to the next stage in the supply chain. Now, at a high level, today's boards have only one trusted component. It's a famous TPM that goes into networking devices or PCs, etc. In the future, every chip has to have a fingerprint, and also the device that they have to have a certificate that essentially has some sort of a trust score. And then the idea is that you're going to have the chip enrollment. You're going to have trusted data that, and provisioning later on that can happen. So trusted data can happen anywhere in the supply chain, from the local servers of each enterprise, like this here, to the cloud. Then you have device onboarding, and then you link all the identities, including the owner identity, because you may go through several distribution channels, but what matters is the final owner, all right? All the way down to the owner identities. And at that point, you have the ability to essentially offer all kinds of services that can be monetizable, for monitoring shipments, monitoring origin and provenance, chain of custody, field use analytics. But more importantly, once you get that part, which is quality and security and reliability, you can start talking about device onboarding and device management that could occur from the chip inside to the extent that you have sensors inside the chip. Okay, without going to too much detail, if you can do that from a chip aside, you can do all kinds of tricks. You can use the BIOS and the process technology to extend the battery life. This is the Tesla trick that they did in Florida hurricane. They sent a provisioning command and they gave another 100 miles. It was very controversial, but that's exactly the world where it's going. We're going to hardware as a service. You can diagnose RMAs inside the chip remotely. You can ship chips, and you can actually provision whether it's going to be Ethernet or Profinet, or depend upon the protocol will be on site. And of course, you can actually ship generic products and security configure them in the supply chain because you have that infrastructure with the fingerprint and the security. They go together. Some of the use cases, I will pass the smart infrastructure. I will start the one you care about. This is a DARPA use case. It was posed as a problem 2 years ago. They say, I cannot carry a tester in my in my plane. And I got all these problems from stress migration, bias temp, erosion, hook carrier. And how do I uncover that? The answer is you got to put a sensor, you got to put security, and you have to have the ability for that plane when it's in the hangar to to securely connect to the cloud and get that data back for analytics. That's another use case that is actually being developed right now by an automotive vendor. Basically, you put a chip that has hundreds of ARM cores, 150, but you put redundancy because you know that 7 of them will fail. So as they start failing, you collect that data, and eventually you open up a channel of communication and you send that data out, and you expect that there's going to be a failure, and that can create a preventive maintenance. This is the classic example. I think automotive would lead on this, of getting test data from the field. This is very important, not only for process voltage temperature parameters, but also architecture data such as how fast is the memory to processor exchange, how fast is the I/O band, bandwidth, how the traffic situations or high contention situations can affect that. Notice I'm talking use cases. It's not about the chip now, it's about the use cases that can be supported by the data. So finally, the way we look at the world is, that we have to connect with standards bodies, and we create these 4 domains of operations, from internal component traceability to external distributed traceability to system internal traceability to external by, again, use case. And you see that there's 2 arrows. The horizontal arrows relate to the digitalization with the handoffs. That has to be tracked. And the vertical arrows relate to authentication that needs to be done in different places. And that's where all the technical standards bodies come in. Because to say that I have regulation, or I have 62443 where I'm a trusted supplier, or I have all these ISOs where, I have the check marks does not mean anything. All right, because you may have rogue engineers, and if you don't put that security and traceability inside the operation, and then each and every organization plays a role here, from basic traceability from a tester, security, JEDA comes in and now says, I'm going to add my data model so that I don't rely on a PDF that says a spec, but is connecting to the operation of that spec. IPC comes in and says, I have bill of materials that carry the traceability. SAE G32 comes and says, okay, I'm going to build a system of systems. So I care about the car connecting to the EV infrastructure and that, the monetization, et cetera. So all those things have to come together. This is really a very ambitious ecosystem, but it's not going to be a one big thing. We have structured it by domains, by little squares. Everybody dancing in the squares, and there is handoffs, receivables, deliverables, process, and handoffs. And as long as we all follow the same methodology, one day we're going to fill all the blanks. All right. With that, I went obviously about 10 minutes over. I just want to let you know that these white papers fall in different domains, all right, to show the connectivity. And when we have time later on, I'm going to tell you what I'm asking. Here you basically have a lot of experts that come from OSATs and testability at the OSAT, and further down packaging, etc. We need those experts to come and review white papers and add their value, because that's the way this is going to be a complete ecosystem solution. So feel free to go to GSA Ties, and you can click the button to participate as a trial. You're going to see all kinds of different papers, and I'm sure those are executive summaries, and I'm pretty sure that some of them will interest you. And if you're interested, let us know, and we'll work with you. That's all for now. Summarize, GSA Ties is about collaboration, acceleration, and end-to-end. Very simple. At the end, we want to facilitate digital transformation and adoption of secure IT services that will be driven by data. Data is the new gold. Thank you.
Thank you, Tom. Let's do some really quick questions. How is this related or built upon or differentiated between the old DARPA Trust program that was, out a little after the year 2K?
Glad you asked this. I was at NDIA last week, and we had the DARPA people, and we had the defense people saying, we represent 1% of the industry. The president and they said, we need to accelerate public-private partnerships. Our job at GSA Ties is to make it as commercial pervasive as possible, but add in the security and traceability concepts that were developed bottom up from a technical standpoint for DoD. All right, so that's very, very important. But when it comes, for example, to data traceability, there is a lot of work that was done by DoD. But on the other hand, if you go to Europe, you'll see a lot of work being done by Gaia X and Katina X. All right. Our job is to look at the best of both worlds and come up with a strategy that pretty much everybody can accelerate. We're a business ecosystem. We're not going to cater only to DoD. Does it make sense?
Okay. And then question was, is this different or the same as the microelectronics quantifiable assurance MQA program?
It is. The MQA is a core part of it, because in order to do MQA, you got to digitalize. You got to digitalize. You got to decide which data to keep, inside private. You got to decide which data you may promote and make it available to data consumers that may interested in having it, in which case there's a lot of licensing agreements coming. If you notice about the digital thread, one of the things that we try to level the playing field so that the hyperscalers that own the root of trust do not control the services. We control the digital thread of data, and everybody who's participating in that data will have a stake in monetizing it, period. As long as I'm in the chair, this is my vow to the ecosystem, okay?
All right. And I think the last question we'll talk about, I think it's at the panel discussion, but it's, how do you deal with untrusted people in the supply chain? But we'll hold that one for later. So, but thank you very much, Tom. I want to thank everybody once again and wish everybody a good rest of their day. So thank you, everyone.